Now, after covering the conditional distributions in the discrete case, we're ready to talk about the continuous case. Okay, so the general format works very similar. We're still looking at the ratio of the joint and the marginal. Okay, and then as you can imagine, compared to the discrete case where we do the summation to get the marginal in the denominator, we're trying to get the through integration, right, to get the numerator. Okay, so with joint probability function of x and y. Okay, so here we're using joint PDF. Okay, can use my regular color here. Okay, the conditional PDF of x given, okay, y, okay, and notice here, okay, so we're just using this as a way to express, okay, the definition. So because we know that, well, the probability of this event has probability 0 because it's a continuous distribution. We use it for conditioning, okay, but what we really mean by this is, as you can see here, if we know the value of y, okay, and we're trying to figure out the conditional distribution of x given y, then that is defined as the joint PDF over the marginal of y. Okay, so this is, like I said, still follows the same general concept of doing conditional distribution. You have the joint over the marginal. So for us, if, okay, they are jointly continuous, then if you want to get a probability, a conditional probability of the random variable x in a particular region A, okay, then what you do, just like what we used to do for the conditional distribution, you're working on this conditional distribution, okay, because x given y, and then you're integrating with respect to x in this particular region. Okay, so think about this, okay, for a second. What we're doing is we're defining conditional probabilities of events associated with one random variable, which is x, okay, given when we are given the value of a second random variable. Okay, so like I said, we're using this just as a way to condition. Okay, we know that the probability is always 0. Okay, but as you can see, when you do the calculation, you're doing the marginal of y, which is not a 0 thing when you specify it. Okay, so so down here, so let me say this. This is the definition. Okay, and down here, this is in practice if you're trying to figure out a conditional probability of a certain event, okay, then you can integrate with respect to this random variable of the conditional distribution in the region A. All right, and then from there, okay, we are able to do the CDF as well. Okay, so CDF, remember, we have this, we use this little a, okay, to represent that's the point that we're evaluating the CDF for. And then what this does is that we're looking at the conditional CDF, right? Meaning that given what the y value is, okay, we're interested in the probability of the first random variable x is smaller or equal to a. Okay, and then in that case, when you do this calculation, okay, just like what we're doing with the region A to get the probability of that event, here you're integrating the conditional x given y PDF, okay, with respect to x, okay, from -infinity to the point that you're evaluating. Okay, so that is the definition itself. So we're just putting it a definition of CDF itself, and then we're putting it into the conditional distribution context. Lastly, if x and y are independent, okay, so that is the new stuff in chapter 6, right? The part 2 of chapter 6. When you're working with continuous random variables which are independent from each other, then if we do the math, okay, so first of all, before doing the math, look at the result, okay? The conditional distribution of x given y actually just the marginal of x, okay? So this is very similar to what we have seen in the discrete case, okay? And also just conceptually, because they are independent from each other, knowing y does not affect your knowledge about x. So that's why the conditional is equivalent to the marginal, okay? But the detail, okay, going through the derivation is we always go back to the definition of the conditional as the ratio of the joint over the marginal, okay? And then the independence assumption here tells us that the joint can be broken into the product of the two marginals, and then you can cancel it out, the marginals of y in the denominator and in the numerator, so you get the fx in the end. Okay, so like we were writing over here, this is the unconditional density of x, okay, which is also just what we call the marginal density of x. Okay, so this independence assumption breaking into the products, we have used this earlier for the discrete case as well. Okay, so keep in mind that this is something new that we're learning in this week. All right, let's wrap it up with an example. Okay, we're given the joint density of X and Y. Okay, and we know the range. Okay, now you know it's very important to think about the range all the time. The question asks you to compute the conditional density of X given that Y equals to Y. Okay, when Y is in this range. Okay, so both of them are between 0 and 1. Okay, and conditional distribution. Okay, conditional density. So we know that the conditional density needs to be the ratio, conditional, you see, easy to write it wrong. So the conditional density should be the ratio of the joint, right, over the marginal of Y, which is being conditioned. Okay, so we're gonna go with this general definition and then do it step by step. Okay, so we start with this first line. Okay, that's the definition. And then we can start do the math, okay? Do the math in particular, because we have the joint, okay? The joint is given to us, okay? We need to figure out the marginal. And the marginal, as we know from before, is integrating out X of the joint, okay? So you can write it in one expression and then doing it step by step. Or if you want to first write it out how to do this particular integration, that's totally fine as well. Okay, and then just take the ratio. Okay, whichever is good, just show all your work. Okay, so the numerator is the same is what we are given. Okay, and the denominator, so notice that there is a constant 12 over 5 over here, so I canceled it out immediately from the ratio, but you can write it out and then just cross it out so we know you're canceling them, but it's a constant, so I directly just drop it all together. But like I said, you would have this 12 over 5 in both places, and then you can cancel it out. Okay, and then the numerator, okay, is X times 2 minus X minus Y. Okay, and then the denominator, as we know, we need to integrate the joint with respect to X within its range. So it's from 0 to 1. Okay, and then X times 2 minus X minus 1. Okay, so you do the integral in the bottom. Okay, notice that you're integrating out X. Okay, so whatever in the bottom should has no X. Okay, that's a way to check your work. Okay, and then you could still have Y, right? Because you have the density function involving Y, and then Y it is still it can stay. Okay, and in this case you do it and then eventually you're right at this point. Okay, so yeah, I think in this case maybe compared to the discrete case, the continuous case is maybe not as challenging, because in discrete case you have to think about all of the different joint probabilities, you have to compute them and then do the sum to get the marginal and then do it out there. Whereas here, if you're given both are continuous and you're given the joint PDF, as long as you specify, so don't forget this ratio, the range, okay, the range of X and Y, and then you do the integration of the marginal and then take the ratio, and then the rest usually just follow pretty in a pretty straightforward manner. And I would just also mention here, we're looking at the conditional distribution of X given Y, right? And if you look at the final answer, you have X and Y. Nothing is worrisome there, okay? Because we're still looking at the distribution about the random variable X given Y, whereas Y in this particular case, you can think of Y as given, okay? But then the random variable is X over here.